Ready.
Okay,
Anytime.
right. So welcome everyone. So today is the last day of this year, and so the first speaker of today is Lei Wu from Leuven in Belgium, and his talk is about demodules, motivic integrals, and hypersurface singularities.
Okay, yeah, thanks for the invitation. And probably because this is the last year of 2021, so I should say Happy New Year to you guys. Okay, so let's get started. Today I'm going to talk about the demodules, motivated integrals, and hypersurface singularities. So first, let's look at the first way I'm going to recall is the way we are studying surface hypersurface singularities by using demodules. So actually, this is called B functions. So B functions are also called Bursa-Sato ideal, Bursa-Sato polynomials. So before I introduce the definition, first let me give you some motivation. So let's assume f is a real value function or a compound value function. So then let me recall the definition of a Manin transformer in functional analysis. So the Manin transform of f is defined to be I use this mf. So Manin transformation maps f to a function in S. The Manin transform of f is defined to be integral from 0 to infinity, and then we take x to the s minus 1, and then we time f x, then we integral with respect to x. Then for example 1, then the Riemann-Zeta function can be rewrite as a Manin transform. Okay, Riemann-Zeta function. Zs, this is 1 over gamma s. Gamma s is just the gamma function. Integral from 0 to infinity. X to the s minus 1 times fx dx. Here fx is fx is 1 over ex minus 1, this function. Okay, so we can use the we can use the Manin transformation to recover Riemann-Zeta function. Okay, so this is the motivation. And next, I'm going to define B function following some similar idea. Okay. So now we assume f is a unvariable polynomial complex with complex coefficients. So f is a x1 xn. And then we consider this algebra dx. So this dx algebra is a non-commutative ring, which is defined to be, we use all the other coordinate ring, but we are adjoint partial 1, partial n. Okay, so because when we take derivatives, then we know there are some relations. So I skip that relation. So that's why I use this square bracket instead of this bracket here. Okay. So this dx is a non-commutative ring, and then the B function of f denoted by BFS is a one variable function. So this function is a variable polynomial. So this is inside this polynomial ring CS with a independent variable s. So is the monic polynomial, sorry, of the least degree, so that this functional equation is satisfied. BFS fs equals P fs, Pxr fs. And P here is sorry. Give me a second. P here is an element inside this bigger array, the polynomial array in variable s with coefficient of differential operators. Okay, so so you may think this definition is a little bit technical, but let me explain this this definition by some examples. So let's look at example 2.
Sorry, I think one exponent is wrong, right?
Sorry.
So PFS plus 1, right?
Oh yes, sorry. Thank you. Yes, of course. Otherwise, it should be a trivial. Yeah, I'm sorry. Okay. So if we take f to be x.
Excuse me.
Sure.
Is for some p or what?
Yeah, for some p.
For some p.
Yeah. P inside this bigger array. Here, let me. Oh, sorry. I'm really sorry. This one. Let me get rid of all the others. To avoid. Okay, so if we take f to be a coordinate x1, and then we know if we take partial one, so partial one is just the vector field along this x1. Then we take partial one x s plus 1, because this is just the we take derivative of power function. So this is s plus 1, and the power dropped by 1, so we get this. So this implies BFS is s plus 1. Okay. So in this case, this B function is very easy. Okay, 2. So now let's make f more complicated. So more singular, I mean, the divisor of f is more singular. So we take f to be x1 squared plus x2 squared plus plus xn squared. Okay. And then in this case, let's try to write out the functional equation. Okay. So we have this f to the power s. So now we use this Laplace operator, partial y, partial I on 1 to n, partial square. So this is Laplace. Anyway, so I think I forgot how to spell Laplace in a correct way. Sorry. Okay. So if we take the Laplace operator and XR f to the power s plus 1, then we get 4 times s plus 1 times s plus n over 2 fs. Okay, so this implies BF s is s plus 1, because the B function by definition is monic, so we can get rid of this part 4. So that means s plus n over 2. Okay, and now the third one. Okay, so now now we take f to be the defining function of a cusp singularity x squared by cube. So in this case, this functional equation becomes more complicated. So I actually this p is a little bit more complicated. So I don't write that down, but I can tell you b function of f in this case is s plus 1 times s plus 5 over 6 times s plus 7 over 6. Okay. So from this example, we can see the B function contains the information of singularities of the divisor defined by the function f, the polynomial the polynomial function f. So the more the divisor defined by f, the more singular the divisor by f is, the more complicated BFS. Okay. So now let's look at theorem 1. Okay, this theorem is due to Bernstein-Saito. Maybe in 17 something. Okay, and then so BFS exists in general. Okay, now let me give you a sketch of proof. Okay. So so to prove this theorem, we consider these modules. consider this dxs generated by fs plus 1. This module is embedded into fs because f is because f is inside this dx. Yes, because a function can also be treated as a degree 0 differential operator. Okay, add this quotient module m equal to dx s fs over dx s fs plus 1. Okay, so now we need to use this fact. Actually, fact 1, this m is a holonomic dx module. Okay, so you might wonder because we introduced this variable t s here. Okay, so that means that the dimension increased by 1, but because we take this quotient here, so we can guarantee m is still holonomic. Add s is give an endomorphism dx endomorphism of m. Okay, and now we need to use another fact 2. So if phi is a element, is an endomorphism of some holonomic module, and it's holonomic D module, then then phi has a minimal polynomial. There exists bs inside cs, so that b phi equal to 0. So because s is the endomorphism of m, so use this fact 2 at fact 1, we get theorem 1. This is the end of the proof. Okay, and we can see here, let me also comment here. So this can be seen as a D module analog of Mailin transformation. Okay, so those two are D module Mailin transform. Okay, any questions so far? Okay, so this is so this theorem told us this B function always exists. Now let me also recall another theorem 2 due to Kashwara and Malgrach. Okay, so if we take exponential of roots of BFS, then we get another set, right? So roots, the set of roots of B function, if you take exponential of that, then we get another set. And this set is identified with the eigenvalues of the monodromy action. Or the cohomology group. Groups of Milnor fibers of F. Okay, so actually, this proof is a little bit technical. So, so indeed, we need to use the Riemann-Hilbert correspondence for nearby cycles, for D modules and for reverse shifts, whatsoever. Okay. Okay, so because the eigenvalues of a monodromy actions are cohomology group of Milnor fibers of F also somehow detects the singularities of the divisor defined by F. So this theorem also means B functions contains the information of singularities of the divisor defined by F. Okay, so this is the first way I want to recall about how we can understand singularities of a divisor defined by function by using D modules. Okay, so next, any questions so far? Okay, so next I'm going to use motivate integrals by following similar idea. Okay, so Next, let's look at motivic integrals and multivisited functions. Well, motivic functions. Okay, so so first, let me recall the definition of a motivic measure. Okay, so we take X to be Cn, the complex of phi space, and then we relate delta M to be spect of CT quotient by the power the ideal T to the M plus 1. Okay, and then we use delta infinity to denote spectra of C double bracket T. Okay. Okay. Then we have a then because this then we have a because we have the inclusion of this ideal generated by T to the M plus 1 to includes T to the M T to the M plus 2 and includes T to the M plus 3. So this because we take spectra the way the arrow changes direction, so we get a inductive system. So inductive system del M minus 1 contained in del M contained the del infinity. Okay. Now we set xm equals harm from del M to X at X infinity to be harm del infinity to X. Okay, so then the because we have harm, so the arrow change again. So we have a induced projective system. Place a projective system. X infinity to xm plus 1 to xm And so we use the pi m plus 1 to denote this map. This map is maybe I should use yeah, okay, pi m. Okay, so if we take, because we are in the alpha case, so we use R to denote the quantity of X. So say x1 to the xm. Okay, and then another way to write xm is just xm is a set of all the jets. Okay, so just the rm from R to, because if we have so this is harm is just a scheme harm. Okay, so scheme harm, because we are in the alpha case, is equivalent to rehomomorphism. So we have R to CT over T m plus 1. Okay, so this xm is also called space of m jets. So gamma m, so this is gamma m, sorry. So gamma m are just m jets. Okay, so xm is also called space of m jets. Okay, at X infinity is similarly just gamma R to C double bracket D. Okay, so this is space of arcs, and this gamma here is an arc. Okay, arcs. Okay. Any questions about the definition? Okay, now let's look at another definition, and we use K0 variety C to denote the Grothendieck group of group of varieties over C. Over C. So that means we quotient relation. So if we have a variety X and we identify x with x minus y plus y. Okay, so here y is a subvariety of x. Okay, maybe I should, because I have too many slash, so I should say modulo. Okay, so this is a group of varieties over C. Okay, so now we set Kc to denote the localization of this variety over C. So we take L inverse. And the L here is just the class of the dimension 1 of phi space. Okay. So this is just the class of a phi lie. Okay. So roughly speaking, so xm is just x times L, maybe, sorry, xm is almost just x cross L to the m n m, and this is just because x is cn, which is just L ln, so this is just L m n plus 1. Nm plus 1, sorry. And m plus 1. Okay, and the fxm infinity is just let me put a Coombe side to indicate that this is just some give you some intuition. Okay. Okay. So now also this is 1, definition 1, the definition 2, and then for a subvariety or subscheme Cm inside Xm, we define the motivating measure. For C by definition equal to pi m inverse of Cm. So because Cm is inside Xm, so if we take because the Xm is a map from let's look at here. So Xm is a map from X infinity to Xm. So if we pull back, then this gives us a set inside a subset inside subvariety maybe inside X infinity. Okay, so then we take the motivating measure mu C to be the class of Cm quotient by L to the n m plus 1. Okay, inside Kc. Okay, so we use this term because we can first pull back Cm to something inside x sub m plus 1. So this term, we use this term to make this definition independent of the choice of xm. And so we can pick x L, for instance, when L is greater than m. Okay. 3. So for Z inside, if Z is a subvariety of X, then we define contact loci. So this is M's contact loci of Z to be pi m or m minus 1 inverse of Z m minus 1. Okay, because Z is a variety, so Z we can consider the arc space with target Z. So this is Z, the m minus 1 jet space of Z. Okay, minus pi m inverse Zm. Okay, so because of eventually we will add up all the Zm together, and we are going to calculate the measure of z infinity inside x infinity in some way. So we don't want to overlap, because if we pull back zm plus 1, then somehow we to infinity to x z infinity, then we somehow like so this zm minus z sub m minus 1 contains some of zm. So this definition kind of this kind of give us a stratification of z infinity in some sense. Okay, so this is exactly gamma. All the arcs, so the arcs from R to CT double bracket T, so that this gamma, the ideal, or IZ is the ideal of Z, okay, is exactly equal to T to the m's power. Okay, so this cut mz is also called the set of m's quartile loci. Okay. Okay, now with all those three definitions, we can define multivariate function. Okay. Questions?
I have a question.
Sure.
Before go further, so that roughly something that it is times L blah blah. Is that for only when X is a smooth case, or even includes a singular cases?
Also,
previous slide, yeah.
So can you say that again?
Here,
Sorry.
roughly speaking, you said Xn. Yeah, is that hold only for smooth?
Yes,
smooth
yes,
locus,
yes,
or?
yes, yes. If Z is singular, then it becomes to be more and more complicated, because if Z is a singular defined by function, it's defined by some polynomials f, for instance hi, and then this hi gives maybe like more functions to define the subvarieties inside xm. If you replace this x by this coordinate ct over t, or c double bracket t. So in general, if x is smooth, then xm at x infinity is also smooth. But if x is not smooth, singular, then xm at this x infinity becomes even more singular.
Thank you.
Okay. Okay. So did I make this number correct? Okay. 2. Motivic data function. Okay, so now we take f to be unvariable polynomial with complex coefficients. Okay. And then we use d to denote the divisor defined by f. Okay, and then motivic zeta function. F is the integral. Actually, it's the Maillet transformation. Maillet transform have fs with respect to the motivic measure. Okay, so but this is kind of give us a intuition. So, but by definition, so this term. This is just the a symbol I used to denote. So the definition, the real definition is this. We take a sum m from 0 to infinity, and then we take the motivic measure of the quartile loci of d. Okay, and then so we also want some variable s in this variable s play some rules. So we take L to the power minus ms. Okay, so this m here is the same as this m. Okay, so inside.
Excuse me.
Sure.
So, actually, I'm not sure how this related to Maillet transformation. Maillet transformation use the s, that f to the s. So how does this related to Maillet transformation?
So this part, I mean, this is also like a, how do we others? This is kind of a, so I can just give you some intuition. I just say this is just, this give us just the intuition, not like 100% sure. So this is because x infinity is kind of given by this. So f, so this term together is kind of give us this fs, and then this sum give us the integral of the multiple measure.
I mean, the relation between the Mellin transformation, because the definition of Mellin transformation is x to the s, not f to the s. So
Oh yeah. So this is kind of for the D module case, if we take a D module OX, so let's go back to the, let me try to explain this in a more clear way. Okay, so this is kind of a, this, I say this is a Mellin transformation, right? Analog of D module Mellin transformation. But this we only give power of f. We give f power s plus 1. But if we want to define Mellin transformation, so this is kind of a Mellin transformation for OX, okay? For OX. And if we replace OX by other D module, then it give us a more general Mellin transformation. So that means same philosophy here. Okay, so that means we take the function to be 1. Okay, if we replace that function by some other things, you can modify this multivisible function by some extra factor. Do you know what I mean? So this is kind of a Mellin transformation for the constant function 1.
Can you give some reference that I can read after your talk, if you know?
Maybe
if you
the
have
next
any
results
good reference for this Mellin transformation things.
I don't know. Actually, this is my thinking, and I think this is
Okay,
this
it's
makes
okay.
sense.
Okay.
Yeah, this makes
Okay.
sense. Yeah. Okay, so this is inside. We have to localize KC because this gave us the infinite this gave us infinite sum, right? So we take some power sum together. So this we have localized. You need to take a complete localization of L minus S. Okay. Okay, but anything, all these multivariate functions is defined by the Neff-Louisa following idea of equals. So you can, so you probably can read the paper, some papers of there are like a bunch of papers written by Igusa and the Neff-Louisa in like maybe 20 years ago. KC L minus S. Okay. So now let's take you. Let's tell you an example. Example 3. Okay. If we take x to be the affine line, and if we take f to be just the x, and then divisor is just the x equal to 0. It's just a point, right? Okay. And then the multivisible function f is summation m equal to 0 to infinity, and then we need to take the class of m minus 1, okay? Sorry, over L to the power m, because n here is 1, okay, minus d m, okay, over L m plus 1. So because d is a point, so the Jep space of a point is also a point, and the arc space of a point is also a point. So this is just a point. So it's 1. So a point in this Gaussian group is just 1. So this is 1. This is also 1. Okay, times L to the minus S. So this is equal to, okay, m equal to 0 to infinity. 1 over L m minus 1 over L m plus 1, the L minus S. So this is equal to L minus 1 over L times 1 over S plus 1. Okay, so from this example, we can see this topological zeta function, the motivated zeta function is not, so it's kind of a convergent, right? To give us a rational function in L at L to the power S. Okay, but in general, this is also true. So now let me tell you the Chedel variable formula. So I believe this is due to conservation. Okay. Okay. If we take pi to be a log resolution, okay, of the pair x comma d, okay, and if we set the pullback of the divisor d equal to some decomposition I from 1 to r. So here is r, not gamma. Okay, alpha I and the ei. Okay, so ei just the exponential divisor or the street transform of of d. Okay, so chi y over x is some. So this is a we can write the relative canonical divisor in a similar way, I from 1 to r. Okay, and then for I, so then we have a set, right? 1, 2, r. So this is the index set. So this is give us the index set of the divisor ei. Okay, and if we take a subset of this index set, then we define ei circle to be a intersection of all ei, I inside I, minus union of ej when j is not containing I. Okay, so roughly speaking, like strictly speaking, sorry. So this all the ei circle give us a stratification of pullback of d. Okay. Also, I mean the shift theoretical pullback. So that means this means we don't consider multiplicities. Okay. Oh, sorry. Yeah. So this is equal to destroy union of all the I inside this index set ei circle. Okay. So there's some notations. Using this notation, we can rewrite multiplicative function. So this theorem is due to, now we have this third theorem due to, I believe this due to the Neff-Lewis. Okay. ZF motivic is L to the minus n summation I inside 1, 2, r. So that we take the class of E circle I, and then we take a multiplication by L minus 1. So remember, Y is just the class of a point. Okay? L is the class of a phi lie. So this is kind of the class of a C star to the power of I, to the cardinality of I. Sorry, the power is just the cardinality of I at times pi I inside I. So that's L to the power minus SAI plus minus. Sorry. Minus Ki plus 1 over 1 minus L minus SAI minus Ki plus 1. So from this Chedel variable formula, we can all see this multiplicative zeta function is always a rational function. Okay. Any questions?
What is F?
F is the divisor. f is a polynomial. So this multivariate zeta function defined for some polynomial f.
Divide by t, division. Okay.
Oh yeah, so this is kind of the defining function of a divided d. Okay. Oh yeah, I forgot to mention. So we have to fix this f here. So the multivariate zeta function is for f. Okay. Define for f. Okay. Now we can take topological specialization. So because from this KC is the Grothendieck group, it localized L minus one. So this is the so we have the KC to Z. So this is the so this is the compact supported Euler characteristic functor. Okay. Characteristic. Okay. So now, so using this compact supported Euler characteristic. So you can check, because we are considering this compact supported Euler characteristic. So the relation, if we identify x with x minus y plus y, then this because this compact supported Euler characteristic is kind of additive with respect to this relation. So this Euler characteristic as a compact supported Euler characteristic is well defined for KC. Yeah. Anyway, so then we have corollary one. Okay. So then the topological zeta function is just the multivariate zeta function taking this topological taking this compact supported Euler characteristic is chi C ZF motivic. Okay. Or because because topological Euler characteristic of L is, because L is just the alpha line, so we know that the Euler characteristic or the compact supported Euler characteristic is just one. Okay. And then this give us I inside 1, 2, and then we have take topological Euler characteristic of EI circle times pi I inside I 1 over ki plus 1. Okay, so this is kind of we have if we take a, let me also explain a little bit more. So if we take L equal to 1, so Euler characteristic, the compact supported Euler characteristic of L is 1. So this part is 1, right? But this part become to be 0. So but this part is also become to be 0. And the product, we have like a cardinality of I factor of the product. So the limit of this over this exactly this by L'Hopital's rule. So this somehow we need to use L'Hopital's rule to get this correctly. Okay, anyway. Okay. Okay, so this topological zeta function is a rational function in S. Okay, but it may have some poles, right? So now let's look at another example. Example 4. If we take F to be the cusp singularity inside C XY, then we know the resolution of the divisor of F is easy, right? So this is just the we blew up the point as we take blow up as the origin 3 times. So this is a cusp singularity. E is street transform of this divisor here. Okay, E1, E2, E3. Okay, and pullback of D is E plus 2E1 plus 3E2 plus 6E3. So if my calculation is not right, please correct me. Ky over x is E1 plus 2E2 plus 4E3. Okay. And then the topological zeta function. So okay. So then we should look at this part, right? At this part, the open part, this part, at this part, at this part, and also this intersection point, this intersection point, this intersection point. Okay. So the zeta function in that case, so we have this 1 over 2s plus 1, because this E1 is P1, right? Because if we blow up the exponential, each of the exponential divisor is just a P1, right? So this E1 is P1, but we have to take away this intersection point, right? Because it's open strata. So we have the stratification is just this part, 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 this part. So the coefficients along E is just a 2s plus E here is 1, right? So 1 plus 1 is 2. So here is 2. Sorry. At times the Euler characteristic of E1. But the E1 minus a point. E1 minus point is just a C. The Euler characteristic of C is 1, right? Times 1. And if we calculate this part, okay, and we know this is just the Euler characteristic of the open part. Get rid of this point, right? Because the open part that give us a covering, 2-to-1 covering to C star. Okay. 2-to-1 covering C star. So the Euler characteristic of this part is 0. So 0 times 1 over s plus 1 plus 1 times this. Okay, let me make this more clear. So 0 times, because the Euler characteristic of C star is 0. So this is the open the complement of this cusp singular cusp away from the singular point. It's just the 2-to-1 covering to C star. So its Euler characteristic is also 0. So we get 0 over s plus 1 plus 1 times 1 over 2s plus 2. So this 2 is exactly this 2. This 2 is just a 1 plus 1, because the ki is just 1 in this case. Okay, and then plus similarly, if we consider this part, we get a 1 times 3s plus 3 plus 1 times 1 over 6s plus 5. And then we have to consider this point here, this point here, this point here. So then we get this term 1 over s plus 1, because the Euler characteristic of a point just 1. So it's 1 times this s plus 2s plus 2. Plus 1 times 1 over s plus 1, 3s plus 3, plus 1 times 1 over s plus 1, times 6s plus 5. Okay. Okay. So the topological zeta function is exactly this in this case for cusp singularities. Okay. Now we are ready to from this example. Remember. Okay. So let me recall the B function of f in this case. So this is the second example in this talk at the very beginning. So BFS is just s plus 1 times s plus 5 over 6, s plus 7 over 6. So we know this term appears here, actually also here. This term appears here. Okay. So we have this monodromic conjecture. Okay. So then let me check the number 5. Monodromic conjecture. This is due to Igusa and the Nefluisa. Okay, so the first one is maybe I call this part A. This is also called the straw monodromy conjecture. Okay, so poles of topological zeta function is contained. So because from this example we can see this 7/6 does not appear inside this inside the poles of the kinetic poles of the zeta function, yeah, topological zeta function. So we only have this partial inclusion instead of identify them, these two sets. Okay, so equal to roots of contained in roots of df s. Okay, and then we have this weaker version. Okay, poles of zf topological is contained in. Oh, so if we take exp, the exponential of this, because the exp of roots of b function are just the monodromy eigenvalues. Okay, so if we take exp of poles of this, so we get contained into monodromy eigenvalues of cohomology groups of monofibers of F. Okay, this is like a theorem by theorem 1. I believe it's theorem 2. Okay, so because exponential of roots of B function is exactly monodromy eigenvalues of the monofiber cohomologies. Okay, so also this by theorem 2 we also know strong implies weak. Okay, and this monodromy conjecture is checked here. Okay, for cusp singularities. Okay, so this is checked for cusp singularities. Any questions so far? Oh, I have a question. I'll check.
May I ask one question?
Sure, sure, sure.
So, so in the form of strong form, so you said the pole of zeta function is, I mean, are roots of, you know, p functions. But do you have anything for multiplicity? Like, I mean, so multiplicity of zeta, yeah.
So actually, because when we define this xm and the zm, we don't count multiplicity, right? And then when we so when we consider this Gaussian group of varieties, we don't consider this scheme structure.
I see.
In some sense. So this is so we don't expect the multiplicity come into picture.
Thank you.
Yeah. Okay. Now the last part I'm going to discuss today is these some null cases for. So this conjecture is way open so far. So for instance, the straw version is only known for curves. When f the divisor is a curve. When n is 2, that means. So for the weaker version, maybe like some case of the surface case is no, but in general, this monodromy conjecture is very open. Okay. So now let's look at some null cases for hyperplane arrangements. Okay. Monodromy conjecture for hyperplane arrangements. Okay. So we consider a polynomial with complex coefficients of n variables. Okay. So this f is called hyperplane arrangements if f is given by a product of Li. So that each Li is a degree 1 polynomial. Okay. And then in this case, so theorem, maybe I call theorem A. Okay. So if F is a hyperplane arrangement, then part A, this is due to Boudou-Mustada-Taylor. Weak monodromy conjecture holds for F. Okay. The second part is due to myself. So this is the only result that is proved by myself. So in this talk, the straw MC for the multivariate, because let me write out the statement, and then I will explain it. It's multivariable topological zeta function of this hyperplane arrangement, of the hyperplane arrangement. Holds. Okay. So let me explain this a little bit. So when we define the topological zeta function, we know this variable s corresponds to f, right? So if you have one f, then we have this s. But because for hyperplane arrangements, this f decomposed into this linear term at Li. So for each Li, we can introduce Si. So yeah, similar way. So we can define this multivariable topological zeta function. I cannot prove the strong monodromy conjecture for hyperplane arrangement in general, but the only thing I can prove now is just the strong monodromy conjecture for this multivariable topological functions. Okay, so this is kind of the, so this part is kind of the multivariable generalization of the strong monodromy conjecture. And then so the idea now is to use this to prove the strong monodromy conjecture for hyperplane arrangements in general. And so there's a critical, there is some like there is just one part need to check. So this is called something called like a diagonal specialization. So the diagonal specialization. So using diagonal specialization, we can use this part to prove the strong monodromy conjecture for F when F defines when F is a hyperplane arrangement. Okay, but there's some like some kind of algebraic property that I don't know how to check to make this specialization process work. So I cannot prove the strong monodromy conjecture for hyperplane arrangements, but I could only prove this strong monodromy conjecture for the multivariable topological zeta function for hyperplane arrangements. Okay. Let me also comment a little bit about the proof of this part A. Okay, this part A is compared to part B is kind of easier, because part A, to prove part A, we only need to know the log resolution of the divisor divided by hyperplane arrangements is completely determined by the lattice structure of the hyperplane arrangements. Okay, then that means all the Di, all this. It means all this AI, Ki are known for hyperplane arrangements. So if the log so I think the main difficulty to prove this monodromy conjecture in general is kind of the log resolution is arbitrary, right? We cannot control Harinaka's resolution of singularity theorem. Okay, but this part A is a little bit easier because the log resolution for hyperplane arrangements. We have a canonical log resolution for hyperplane arrangements. The monofibers of hyperplane arrangements are also known very well. But yeah, but B functions of hyperparameter elements are still very complicated. So that's why this part B, the strong mononomial conjecture for hyperparameter elements is harder. Okay, so I think I'm going to stop here. Thank you.
Thank you for quite good talk. So does anybody have a question or comments?
So but for your theorem of T variable version, so as far as know the B function, the set of B function would be a kind of variety, right? So
Can you say that again? Sorry, I didn't quite hear you clearly.
sorry. So the zero locus of B function for the variable would be a kind of variety.
Oh yeah, so for B, so to formulate the strong mononomial conjecture for multivariable topological zeta function, we need to use a Bose-Sato ideal instead of a Bose-Sato polynomial, because we take factorization of F, so we can define Bose-Sato ideals for this factorization L1 L degree F.
Yeah. So the meaning of the theorem B is the variety is inclusion. You mean, is that true?
So can you repeat again?
So the theorem, the whole means the theorem A part B, your theorem is in the inclusion relation you proved, right?
Yes, yes. So because the conjecture is the conjecture itself is an inclusion instead of an equality between those two sets.
Okay, thank you.
Okay, okay. Yeah, we will. So because of the example of cusp singularities, we cannot expect these two sets are exactly the same, right? We will only have this inclusion. So that means that maybe the motivic integral way to measure singularities of hypersurfaces is more refined. So it can like it has more refined information in some sense. I mean, oh maybe B function is more refined, but it's kind of relative, right? So this one way or another. I'm sorry.
So can you guess what kind of parts are missing? So it's not proper subset. It's a proper subset, maybe in general, right? So yes, so can you guess what kind of parts are missing for the inclusion?
Okay, let me explain this by this example. Okay, why? Let me explain why we cannot expect this 7/6. Also, why this 7/6 should not be C by poles of a topological function. This is because this you can see this is 5/6. We have this root 5 minus 5/6, and we have this 1 minus 5/6 is 1/6, right? But this kind of fs is a power function, so it's kind of defined by, we can define this power function by this log function, right? But log function is periodic, so 1/6 plus 1 is what 7/6, right? So this roots of B function satisfy this phenomenon in general. That means this 7/6 is like a derived, is a roots derived from 5/6 by this pattern.
Okay, thank you.
So this means the roots, some of the roots are kind of like more intrinsic, but the other roots are kind of derived from the other roots, because of one, this root's 1. If we play the same rules, and then we get 1 minus 1 is 0, 0 plus 1 is 1. So 1, kind of the conjugate 1 is 1, but the conjugate of 5/6 is kind of 7/6. So 5/6 is more intrinsic. 7/6 is kind of a derived. So this derived roots cannot be seen by. In some sense, I mean, because I don't know how to prove this mononomial conjecture, so I just give you some idea. So why the 7/6 should not be a root of the zeta function, of the topological zeta function. Okay? I hope this answers your question.
Oh, thank you. Yeah.
Any other question? Okay, then I have a question.
Sure.
So I'm not, I say, yeah, I'm new to this monodromic conjecture and zeta functions. So do you have any, I mean, is there any relation between the LCT and the poles of zeta function? Like, I mean, you know, LCT is always the root of
Yes.
B function. So
Yes.
like, I mean, LCT is always a pole of zeta function?
No,
or
this is
no?
not true, actually.
not
Let
true.
me think. I think there are counterexamples that even LCT may not be appear to be a pole of the topology.
Okay, thank you. And the other question is this monodromic conjecture known for like free hyperplane arrangement or like Cox-sector hyperplane arrangement and so on? Any
Oh,
other?
so yeah, so I forgot to mention so the Vic version for hyperplane arrangements is completely known. But the straw version is only known, for instance, known for free or tame hyperplane arrangements. So if we put more condition, more restriction on the hyperplane arrangement, for instance, if the hyperplane arrangement is free, then the straw monodromic conjecture is true. Is tame. The hyperplane arrangement is tame, then the straw monodromic conjecture is true.
Okay, thank you.
But in general, it's not known.
Who proved for a free hyperplane arrangement?
I think Woolly Wasser proved the free case at tame case. Tame implies free.
I see. Okay, thank you. Okay, any other questions or comments?
May I ask you a very elementary question?
Sure.
So why do you introduce affine line L in this motive iteration?
Say again, sorry.
No. Why do you introduce L, capital L?
Oh, yeah.
Why do you introduce that one in this theory?
Yes. So roughly speaking, this is because of the decomposition. Yeah. So let me try to find it out. Because the philosophy of a Gaussian group is kind of a cut divisor, cut varieties in a constructible way, right? And so because if we cut, then every divisor, every variety should be like a combinations of this L1 or a point.
I see.
So that's why we need to use L1 at the point 1. So that's why we in the formula we have this term L minus 1, because this is C star at this L term, at this EI term. So because the fibers of the XM and X infinity is kind of some big powers of L. So by the definition of the Gaussian group of varieties over C, then every variety should be something can be like rewrite as combinations of L at a point at some product of some L minus 0.1 whatsoever in a controllable way.
Then why do you say L inverse, L minus 1? Why do you?
Also, so because by definition, we have to take infinity, right? So we take because by definition motive integral, we have to take infinity until we go to the infinity. So we go to infinity, give us that means that we have to take L to the infinite power, right? But infinite power, so that's why we need to use this part. Okay, we actually need to take like the completion. Sorry, here completion with respect to X to the minus S.
Okay, thank you.
Sure. In this definition, to make this motive measure modified, so we have to inverse X L, and to make this summation modified, we need to take this completion. But it turns out this completion is kind of extra, because it's kind of give us a rational function by this variable formula.
Thank you.
Sure, and then also maybe let me comment a little bit more. So if we take because by the definition of this motive measure, so we use this this C double bracket T, right? But if we are kind of more interested in this arithmetic way, then we can replace this del M by ZP, the periodic numbers. So this delta, this CT can be replaced by the periodic integer ZP. Then we have this, then the mu is just some hard measure. In this like a periodic, in this periodic setting, and then then we have this Igusa zeta function, which is defined similarly, but it counts solutions modulo p at p squared at p cubed. Okay? So some similar. If the divisor, if f is defined over z, then we have some kind of a Igusa version of the zeta function. A Igusa version of the monomer conjecture, which is similar. Okay? Actually, this is the origin why we define this Tabarro zeta function, because it's kind of some. If you have some motivic to dominate everything downstairs, then if you take specializations a lot different directions, we have different version of motivic monomer conjectures, different version of monomer conjectures.
So you mean Igusa's periodic one is earlier than Konchevich's motivic integration?
Yes. So Konchevich's motivic integral is kind of similar, right? By replacing ZP by C double bracket T.
I see. Okay, thank you.
Sure.
Thank you so much.
Sure.
Any questions or comments? Okay, let's thank the speaker again. Thank you. Very nice talk.